Good morning. Good morning, everybody. My name is Oluwakemi Olobawinu, but you can refer to me as Dr. Winu. I'll be teaching you chemical equilibrium. And at the end of the class or at intervals, I would allow us to have some questions. I've sent the slides ahead and a note ahead so that we can follow together along. Okay, so let's delve into it. This is the book that I used mostly to develop this slides and this note. Chemistry, the Central Science. I think it's on
Can you
sale.
check your slide bar? I'm not sure we are seeing what you are sharing.
Okay. Yeah. Oh, screen. Okay, no wonder. Can we see now, please?
Yes, we can see your slides.
Okay, so this
Thank
is
you.
thank you, sir.
So I'm off. You.
Okay, so this is the text that I use. This is there are two different editions that are right here. But whichever one works, they are not that much different. So without much ado, let's delve into the discussion of the day. So we've studied chemical reactions, and we know that a chemical reaction is consists of looking for new substances from old substances. So the old substances called reactants forming product. So this is a typical representation of a chemical reaction. Now, if you're carrying out your reaction in a place, in a closed system, you put your substance and you fill it all up in a closed system. That's what we refer to as a closed system. It is possible that the products, which is C and D, combine back together to form the initial reaction. So initially, we're going from A and B, C and D, and then because nothing can escape the system, no form of matter can escape the system, which is why we call it a closed system, C and D can also recombine to form A and B, which is actually the case with most reactions, if not all, as long as it's in a closed system. As long as nothing is allowed, the products can combine to form, the reactant again. Such reactions are called a reversible reaction. So the general way to write it is to write A plus B reversibly going to C plus D. Reversibly going to C plus D. And this sign, the symbol right here, is used to show that we are dealing with a reversible reaction. There are common examples in many examples. I just wrote two examples here. Now, what is the condition for equilibrium? So we said you are dealing with chemical equilibrium. So the first thing is that your reactant must have some form of reversibility. So we say that a reversible reaction is a chemical reaction where reactants form products that in turn react together to give the reactants. Anyway, equilibrium means balance. What makes a reaction to be in equilibrium? The fact that a reaction is reversible does not make that it is in equilibrium. Equilibrium in itself means balance. So let's look at our reaction A and B going to C and D again. We recall that the rate of a reaction is related to the concentration of the substances reacting to form products. Now, if we consider the reaction A plus B going into C and D, the rate of that reaction, which we refer to as the rate of forward reaction. So the rate of forward reaction is the rate of A and B going to C and D. And because after some time, C and D also combine to give A and B, then we also have the reverse rate of reaction, RR, which is proportional to the concentration of C and the concentration of D, going back to the product. After some time, because it's a closed system, because it's a closed vessel, since nothing is coming out, the rate at which the forward A and B are going to C and D becomes equal to the rate at which C and D comes back to A and B. In that case, we say that we have achieved equilibrium. So equilibrium condition is when the rate of the forward reaction is equal to the rate of the reverse reaction. We say that the system is also dynamic. It's dynamic in the sense that, so let's look at this picture. At the beginning of the reaction, where we have only the reactants, the rate is high, and then it becomes smaller before it becomes constant. The rate of the reverse reaction, there was no product at the beginning, so that's why it is 0. That as you continue, it also becomes constant. So a time appears where RR equals RF, and that's when you say that your system is in equilibrium. So we say that the system is dynamic in the sense that the forward reaction is taking place, the reverse reaction is taking place. It's not that there is nothing taking place any longer. So it's dynamic because reactions continue to take place. That's why we say it is dynamic. It's not static in the sense that nothing is taking place. One other thing that we note that at equilibrium, the concentrations of your substances, both the reactants or the products, becomes constant. They are not equal to each other. The rates are equal, concentrations are constant, not equal. So that we need to note. Also, we remember it only occurs in a closed system where substances are not allowed to escape. We will see what happens soon when substances are allowed to escape. Okay, so if that's the case, so how do we relate all this to equilibrium, the rates and equilibrium? How do we relate all of them together? The law of mass action. There's something called the law of mass action, which states that the rate of a chemical reaction is proportional to the active masses of the reactants at constant temperature. Now, this law is different from what we encountered in chemical kinetics. Chemical kinetics says the rate is directly proportional to the concentration, but the form is different. The active mass of a substance is the amount of substance which is reactive in the sphere or the volume of the reaction. So whatever you put in, and it is related to the coefficient of the reacting species. So for example, according to the law of mass action, if we consider this reaction, the rate of the forward reaction is directly proportional to the active sphere of A and the active sphere of B. So everything here is A raised to power A, B raised to power B. So that's the difference between the law of mass action and that of the regular rate of reaction. If we are to look from kinetics, we're going to say the rate is directly proportional to A raised to power a certain concentration, B raised to power some other exponent, and N and M need to be developed or to be solved from experimental details. This is different from mass action. It is raised to the power of the coefficient of the reacting species from the balanced stoichiometry of the equation. Okay, now this is the rate of the forward reaction. This is A raised to power A, B raised to power B. The rate of the reverse reaction is also, this is the reverse reaction, C and B going back to A. So you have C raised to power C, concentration times the concentration of D raised to power D. If we add other species in the system, like for example, this is plus E raised to power E, so this will continue to be E raised to power E. But since we're not dealing with that, we're sticking with our hypothetical situation. Now, so we can also write this where Kf, proportionality constant, those are the proportionality constants, they are called affinity constants. Again, they are different from rate constants in kinetics. The proportionality constant and the affinity constants and the rate constants are different. Okay, so from the last slide, we said that equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So this is our rate of forward reaction, so we slot it in here. Rate of reverse reaction, we slot it in here, and we obtain that Kf, A raised to power A, B raised to power B equals Kr, C raised to power C times D raised to power D. So what does that give us? If we put the rate constants on, the affinity constants on one side and the concentrations on one side, we get this ratio. The ratio is called the equilibrium constant of a reaction. So the equilibrium constant is the rate of the forward over the rate of the reverse reaction. That is equilibrium constant. Is the equilibrium constant given the symbol K equilibrium at that temperature. If you change the temperature, the equilibrium constant, the value of the equilibrium constant changes, but the expression remains the same. This is the expression for our equilibrium constant. Okay, so let's look at some examples on how to write the equilibrium constant for a reaction, given that all you need to do is the rate of the forward reaction is given by this. So this is our forward reactant. One substance going to that. And the rate of the reverse Kr, NO2 raised to power 2. This is where we have our 2. At equilibrium, Kf, the rate of the forward is equal to the rate of the reverse reaction. Rate of the forward Kf is equal to that. Rate of the reverse reaction, that is it's given here, Our equilibrium constant is Kf over Kr, and it is rearranged to this. Now, a little bit about units. If we are to look at this, the unit of concentration, which is molarity, is mole per dm cubed. So if we look at this, this is mole per dm cubed squared over, because we have 2 of this, raised to power 2 over mole per dm cubed. However, in writing equilibrium constants, the unit is often omitted because equilibrium constant is defined with respect to activities. And when you're looking at activities, the units cancel out. So most cases, you will see equilibrium constant written without units. Without units. Activities are usually for direct situations. More, let me see, any question from the chat room? Okay, no questions. Please, so that in case people are writing questions, I think at this point, people should stop writing their names. Okay, so moving on, so more examples. Just remember K equilibrium. This is what to remember. Is stoichiometric mole of product divided by stoichiometric mole reactant rate with the power of their stoichiometric mole. So product 3O2 raised to power 3 over ozone raised to power 2. That's the K equilibrium. Similarly for the others, NO raised to power 2 over Cl, that's coefficient 1, and NO raised to power 2. The third one, all aqueous, CdBr raised to power 4 over Br that. And the fourth one. So 2 minutes, please, if you have any question, let's see them in the chat room. Okay, no, we're following. Thank you. Now let's see. Let's see how we. Working with equilibrium constant. Working with equilibrium constant. One thing to note, anytime you want to work with equilibrium constants, let me go back. That's something that we need to include. If you want to calculate K equilibrium, I don't know why my slides are not obeying me. You want to calculate K equilibrium. So in some textbooks, let me say that they write it as KC. K equilibrium, you need to, so that's the concentration of products raised to power P over concentration of reactants raised to power R. It is important to know that we need to work with equilibrium concentrations. Not with just any concentration, but equilibrium concentration. So let's work with an example now. So I think I'm on slide 11, page 5 of your slide. Calculate the value of the equilibrium constant for the reaction below at given that 0.0 0.198 moles were present in a 2.0 liter reaction vessel. So the first thing to always do is to write in such a situation, let's write the equilibrium constant for the reaction. So it's a balanced reaction. Let's see, CO2, CO, so O2, there's 2, 1, 2. That's H2, there's 2, 1, 2, carbon. So it's a balanced equation. That means our equilibrium constant expression is correct. There are no coefficients, or the coefficient is 1 in all cases. So the second thing is, let us determine the equilibrium concentration of each species involved. Equilibrium is molarity, that's concentration, unit for concentration, is number of moles over volume in gm cubed. So we have that's N over V. From the equation, we are given the number of moles for CO2, number of moles for H2, number of moles of CO, number of moles of water vapor, and the volume of the reaction vessel is 2.0. And from that, we know that it's a closed vessel. Okay, in that case, let's calculate the concentration of each one. For CO2, the concentration is 0.1908 moles divided by 2.0 mole. So we arrive at 0.0945 mole. In a similar way, we can calculate it for what H2. H2 is from the equation 0.098 moles of H2 divided by 2. We arrive at 0.45. For CO, it's also given in the question, and for H2O, also 0.0092. So these are our equilibrium concentration. So our equilibrium concentrations, we substitute it in the equilibrium. Apologies, this should go up a little bit. If you substitute it, 0.046 times 0.046, that's what we obtained from here, divided by 0.094. So this is the value of our equilibrium constant. Again, it is okay to be unitless. Now, when we are dealing, for example, here we're dealing with gases. That's just what we just saw. When we're dealing with gases, any question? So I don't understand the solutions to the concept check. Please be specific. Which concept check? So this was the concept check. We are to write the equilibrium constant expression. So here, the question is, just write it in your slide. Write the equilibrium constant expression for all the reactions. So this is the equation of, this is the standard way to write it. Look at the product of all the products, and then divide it by that of the reactants. The product is 302. I'm going to look at this two only so that we can move on. The product is 302. So that means K equilibrium will be product O2 The stoichiometric mole is 3 over O3. The stoichiometric mole is 2. Same thing for the second one. So that's what we have. For the second one, so that is product is NOCl raised to power, the concentration raised to power, the stoichiometric number of moles, that's 2, over the reactants are, there's only one product, so that's where we're moving on, over Cl2 concentration raised to power 1 times NO concentration raised to power 2. This one has 2 products, so 2 products, 2 reactants, so that's H2O raised to power 6 multiplied by NO2 raised to power 4 divided by NH3 raised to power 4 times O2 raised to power 7. So that starts with the concept check. So any other question? What if either of the state of reactant or product? So we are going to get so let me see the comment here. Let me start from here. Please, go back to the slide. I don't know what slide. Why is it okay to be unitless? Unitless because we are dealing with activity. Yes, I said that mathematically. No. So somebody said mathematically this would be dimensionless because their units will cancel out. It will only be dimensionless if you have the same thing, but it will not always be dimensionless mathematically. But because we are dealing with activity, that's the important one, activity. We've already defined activity is just everything in the reaction sphere. I don't want to go further into too much of it because that's not what we are talking about. But just remain that because equilibrium constant is defined with respect to activity, that's the origin of equilibrium constant, it is usually written unitless, not because mathematically it will cancel out. So can we cannot see the solvings properly. I don't know which one is that. Can we get the slide? The slide should have been sent to you. What about the units? Shouldn't we just talked about that? Last week we did first order reaction and others. I just want to ask if the K rate constant is different from affinity constant, is different from equilibrium constant. I hope I'm not on mute. I don't think so. Somebody would have said it. So that's different. That's why I said in the earlier state that. So let me put it this way. I have sent in a small note and a slide to you, please. So, but equilibrium constant is different. I can't write on this place. What is also a unit? I don't know. What if the state of either of the reactant and product? So we get to that in a minute if we don't keep asking questions. Can we have substances in liquid state? We would get to that. What if they are in different states? If we can get concentration, are we to multiply by the coefficient of in the reaction? If we get the concentration, we'll multiply by what's in the reaction. Can you explain more why a reaction that is reversible may not always be at equilibrium? It depends on the state. If it's at the beginning that you just put the reactant, the rate at which forward and backward are coming together, if they are not yet equal, it is not yet equilibrium. But the moment they become equal, then it's equilibrium. If we get concentration, are we to multiply the, so there's some repetition questions here. Can we all get the affinity constant, the velocity or speed constant? No, we can't call it that. Okay, so moving on. So let's work the second example, the next example. Okay, so I think I already talked about this. Use equilibrium concentration. Okay, equilibrium can also be expressed in terms of when we're dealing with gases, we talk about equilibrium constants in terms of pressure. When we're dealing with gases, I think, oh goodness me. When we're dealing with gases, just like in the last example, equilibrium constants can be expressed in terms of pressure. And when it is that case, in terms of pressure, okay. So, and we give it the symbol Kp. So if all our reactants are gaseous, which is what we'll be talking about. I'm not going to be talking about reactions involving a mixture. I'm not going to talk about equilibrium constant. So, but let's follow. We will get to some of those questions are things that we will deal with ahead. So equilibrium constant in terms of partial pressure is given by that expression. And what is P? Okay. So the P of any substance is, in this case, is the partial pressure of the substance. Partial pressure of a gas in a mixture of gases. So partial pressure is another form of specifying. So partial pressure is a form of specifying concentration. You know, concentration talks about the amount of substance present in a vessel, container, or anything. The gases exert pressure. So we talk about the concentration of gases in terms of pressure. If you have more than one type of gas in a reaction vessel, you will talk about their partial pressure. That is the pressure that species exerts as if nothing else is there. So that's its partial pressure of the gas. So in terms of partial pressure, so this equation, we have it as partial pressure of NH2. It's the same thing. So in terms of partial pressure, we still consider products over reactant raised to the power of their number of moles in the balanced reaction. So consider N2 plus H2. This is the process used to produce ammonia. So you have partial pressure NH3 raised to power 2, partial pressure of ammonia raised to power 2, divided by, that's the only thing in the product, divided by partial pressure of nitrogen. So this is not supposed to be there, apologies. Times the partial pressure of hydrogen raised to power 3. Please cancel this from your slides. Another example, the reaction N2O4 going to 4NO2. So products PNO2 raised to power 4 and PN2O4 raised to power 2. Now, for the person that said that mathematically it will cancel out, so if you look at this, the partial pressure, one of the units of pressure is ATM, which is atmospheres in terms of atmospheric pressure. So you see, this one is atmosphere squared. This is atmosphere cubed times atmosphere raised to power 1. So cancel that again. So that's atmosphere. So it doesn't always cancel out. However, it is written unitless. Okay, there's a relationship between K equilibrium and K in terms of partial pressure. So we can have a relationship between K equilibrium and K in terms of partial pressure. What is that relationship? All of us are familiar with this equation dealing with ideal gases. Ideal gases are gases that behave in a certain way under certain conditions, and we call them ideal gases because of how we have defined them. So we recall that so our pressure can be given in the form of this. If we make pressure the subject of the formula, nRT over V. Concentration is defined as number of moles per volume. So which is this nRT over V? And that's the symbol for concentration. And if you put X, that you're saying that the concentration of X. So that means the partial pressure is concentration times RT. R is a gas constant, and our T is the temperature. So for the reaction that we have, for this given reaction, our partial pressure equilibrium constant is given by that equation. Product, see? Product concentration, partial pressure over partial pressure reactants multiplied by the number of moles in the balanced stoichiometry. So if we put this definition for here, so that means that you would write Pc is Nc over VRT times N, so raised to power C, times Nc over Nd over VRT. That's for the species D. So let me just put it out there. So this one is Pc, this is Pd, this is Pb, and that's Pa. You know, mathematics likes to simplify things. So if we try to simplify it further, so just bringing out this loss of indices, A times B raised to power 2 is equal to A raised to power 2 times B raised to power 2. So Nc, so this is still the partial pressure of C. This is the partial pressure of D. This is the partial pressure of B, and that is the partial pressure of A. I'll check your question soon. So remember from our definition, concentration is N over V. So this is concentration of C, concentration of A, concentration of D, concentration of B. So that's all written here. Concentration of C, concentration of A, and then we have all our RTs on one side. Again, loss of indices, we can write that RT raised to power, so this is equal to C, D, D, over A, B, B. This whole expression is equilibrium constant that we've defined earlier. And then this other side, RT, C plus D, from loss of indices, which is what we have here. Further loss of indices is included. So we can write that our Kp is Kp equals to that, Kp equals to that, Kp equals to that. So our Kp equals K equilibrium times RT raised to power the difference in the number of moles between the products and the reactants. Of course, it's obvious. If N is 0, Kp will be equivalent in value to K equilibrium. Question? Okay. Okay, so let's work example. Okay. Yeah. So we're given this reaction system. Calculate the reaction for K. The reaction for the formation of nitrosyl oxide is given as that. These are the equilibrium pressure. We have to calculate Kp and K equilibrium. Equilibrium constant expression for the reaction in terms of partial pressure is as given. So if we substitute the values that we have, 1.2 for NOCl raised to power 2, 5.0 for NO raised to power 2, and 3.0 times 10 to minus 1 for Cl. So we arrive at this value. The equilibrium constant, K equilibrium, is given by that. And delta N is, because we are trying to look for equilibrium constant, we make it the subject of formula. Delta N, let's look at the reaction. There's 2 on the product side, 2 plus 1 on the reactant side. That's 2 into minus 2 plus 1, which is what we have here, minus 1. So our temperature is 298, and the gas constant. So gas constant is 0.8. So this gas constant has the unit of atmosphere liter per mole per Kelvin. It doesn't have the unit of joule per mole per Kelvin. And we have used this value of R because of the original units of the pressure. Okay, please, let's look at some features of an equilibrium constant before today's class is over. And then we'll work some more examples next week. Okay. Some features of equilibrium and equilibrium constant. The first one, so this is, for those of you that already have the slide, I've jumped some slides. I'll come back to them next class. This is page 11, slide 24. First thing, that equilibrium can be reached whether you put so if you consider equilibrium can be reached from either direction. So if you consider this kind of reaction, so A plus B reversibly going to C plus D. If you put C plus D in the reaction vessel first, and they form A plus B, then after some time, A plus B will start to form C plus D. So equilibrium can be achieved from either direction. It doesn't matter whether you start with the product or the reactant. Then the value of equilibrium constant at any given temperature does not depend on the initial amount of the reactant or product. It's only, so see this table as an example. Regardless of the number of moles, this is the starting concentration of this is the starting concentration, this is the starting concentration. At equilibrium condition, this varies a little. but the equilibrium constant remains the same. You see, this one and this one are almost the same thing. I need to verify that. But anyway, the important thing is that regardless of your starting conditions, the equilibrium constant remains constant. The only thing that will change it is a different temperature. It only depends. It does not depend on inert substances. Inert substances are substances that do not take part in the reaction. An example is a catalyst. A catalyst speeds up a reaction, or in other cases, it slows it down, but it does not take part in the reaction. So it's an inert substance as far as equilibrium is concerned. Now, the equilibrium constant expression that we said, calculating equilibrium, is only valid at equilibrium. If you are calculating the concentration using the equilibrium constant expression at any other point that is not equilibrium, you are only calculating what we call a reaction quotient. It's not the equilibrium constant. Some other features, the value of the equilibrium constant, if it is high, remember, K equilibrium is product over reactant, RP. So if it is high, so that is more than 10 times, more than 1,000, then it means that this ratio is greater than 1, and then you have more products. So reactants go into product. If it is high, then we say that equilibrium A to B is more to the product side. If it is low, less than 10 raised to the power minus 3, then you have more of the reactants. And then if it's intermediate values between these two, then you have more just all of them being together. For example, this is a very high equilibrium constant, meaning that you have more of COCl2. So this one is, you have both mixtures almost equivalent. So anytime you take something, you would have a substantial amount of both reactants and the product. Now this is small, and this is small. This is very small. Okay. Then the last one, what's the time now? Any question before I move on? It is 25, not 23. I don't know what is 25, that is not 23. Oh, temperature is 25 degrees Celsius. Okay. Okay, so that means we'll slot it in then, please. Thank you. I would look at that. Mathematics, still on the unit. In the example that you gave us, we had to calculate concentrations ourselves before inputting them into the equation. We use the concentration mole per liter, but if we use mole per dm cubed, the answer will be different. That's not true. Liter and dm cubed are the same. So does the unit of the values we calculate before finding equation matter? I'm not sure I understand that question. But mole per liter and mole per dm cubed are the same thing. So engineering, sequel to all the chemical reactions I've been using as an example. How do we figure out which is static or dynamic? Or we have been running. So a chemical reaction is always a dynamic process. So you won't say that when you're running a chemical reaction, the reactions are constantly reacting. Well, I don't understand the last concept, ma. I don't know what the last concept is. So 23, 25, please. Which example is that? I will check into it, please. So, but if it's if the question says 25, please, we use 25. Now, how did you find delta N in the example? Delta N, you look at the equation of reaction. You are considering only the number of moles. So you are not looking at the number of particles. You are looking at the number of moles of in stoichiometry. So A, small letter A times big letter A, the number of moles is A. So the total number of moles of products minus total number of moles of reactant. Sorry, the temperature in the previous question, please. I have noted that. Thank you. Does temperature matter when solving equations, or it depends? I'm the only one who can't hear the lecturer. Sorry, I can't help you with that. No, I also can't hear. For the answer, that is 36 is at equilibrium. I don't know what that is. When the product is high, equilibrium is meant to shift to the right. But the arrows was showing otherwise. Okay, so now you are talking in terms of concentration. We're talking about what does it mean when equilibrium constant is high? That's what it means. That's what we're talking about. When we're talking about the effect of removing concentration and dot, then we'll now talk about that. How did you get R constant, ma? Thank you. So R is a universal gas constant. It is a constant. It's not something that I derived. So it's one of the things that you look up in the table of constants. Yes, you used R as 0.08. Yes, I said the reason why I used the 0.08 because the original units of pressure is in atmospheres. The R, if I have used R as 8.312, the unit of pressure in that is Pascal. Okay, can I take 15 more minutes of your time, or you have another class? Please type yes, because it's 10 o'clock. At this rate, we're going to, okay. No time, we have another class, continue.
You have another class, so.
I said type it, simple instruction, type it. Obedience is one of the reasons why we have in this mess. Okay.
You have another class, ma.
Oh.
I'm the one who can talk here.
All
yes,
right,
thank
sir.
you.
Okay, no problem. In the questions, ma, would they give us the unit of R? Yes, please. Yes, so I have known that it was my oga. Thank you for telling me. Any other question? Okay, so next class, we'll try to start and move faster. Thank you very much.